Hello and welcome back to Educator.com and welcome back to physical chemistry. So today we're going to start our discussion of statistical thermodynamics. Let's jump right on in. Okay, so I wanted to go through this big picture of what statistical thermodynamics is so that we know why we're doing this. What's our overarching goal? What is it that we're trying to achieve? So our big picture goal is going to be the following. Let me actually work in blue today. So, our big picture goal, it is to find a way to express the thermodynamic properties of a bulk system. And by bulk, we mean just a bunch of particles, like a block of wood, as opposed to the individual molecules that make up that wood. So of a bulk system. In other words, the energy, the entropy, the enthalpy, the Helmholtz energy, the Gibbs free energy, all of these things, the constant volume heat capacity, and the pressure, the basic thermodynamic functions of a bulk system, our goal is to express these properties in terms of the properties of the particles that make up the system. Excuse me, particles that make up the system. So that's what we're doing with statistical thermodynamics. We started the course with classical thermodynamics. We moved on to quantum mechanics. So quantum mechanics, we were dealing with the individual energies and properties of the individual particles, atom, molecule, whatever it is. Now that we have quantum mechanics, we want to go back and we want to explain what we learned in classical thermodynamics via the individual particles. That's it. We're just closing the circle, like we talked about in the overview of the course. Okay, so our primary tool, you know what, I think I'm actually going to go back to black here. Sorry about that. So our primary tool in this investigation is going to be something called the partition function. Our primary tool will be something called the partition function. You know what, let me actually come over here. Called the partition function. And the symbol for the partition function is going to be a capital Q. It's going to be the partition function of the system. Okay. What we're going to do is we're going to express the thermodynamic properties in terms of Q. So we will express the thermodynamic properties, the ones that I listed above. We're going to be listing those, we're going to be expressing those properties in terms of Q. Having a little difficulty talking today, sorry about that. In terms of this capital Q, the partition function. Okay, now we then introduce small q. We then introduce small q. This is called the molecular partition function. Okay. What that means is, or I should say that is, the partition function for each particle in the system. We can actually do that. We can write this thing called a partition function for each individual particle of whatever system we happen to be dealing with. It's pretty extraordinary. In fact, it's very extraordinary. For each particle of the system. Okay. Now, we will express Q, capital Q, the partition function of the system, in terms of Q, small q, in terms of Q. We will then have exactly what we wanted. We will then have, finally, our direct relationship, our direct relations between the thermodynamic properties of the system and the particles that make up the system. That's it. Particles that make up the system. That's our big picture goal. That's what we want to do. So we want to come up with this thing called a partition function. And we want to come up with this thing called we want to find the various partition functions for whatever quantum mechanical system we're going to happen to be dealing with. And again, we already talked about it. We talked about the particle in a box. We talked about the rigid rotator, the harmonic oscillator. These are the partition functions that we're going to look at. These are going to be the partition functions of the molecules, and they're going to express the thermodynamic properties that we learned about back when we started the course. Okay. So let's see what we've got. Let us